Today we are going to talk about an introduction to diode circuits and introduce some models that we'll use in our circuit analysis. So from a circuit analysis perspective, a diode is nothing more than a two-terminal electrical component that uses a rectifying junction, so either a PN junction or a rectifying metal semiconductor junction that conducts current primarily in one direction. Our circuit schematic symbol for a diode is as follows. So over here on the left-hand side, we have our anode. On the right-hand side is our cathode. Our diode voltage VD will have the positive polarity terminal at the anode and the negative polarity terminal at the cathode. So the way that I like to remember particularly is that the big horizontal, or I guess the vertical line in this case, but the straight line is the negative polarity terminal. On a physical diode, it's usually designated by a silver stripe as the negative polarity terminal, which you guys will figure out once you start taking the lab and all that kind of jazz. Our diode current ID, like so, is assumed to flow in this direction. And the first model that we are going to use in our diode circuits is the Shockley or the exponential diode model. Okay. So Shockley or exponential diode model is as follows. Our diode current ID is going to be equal to the area of our junction times our reverse current density JS times the exponential of our diode voltage VD divided by our thermal voltage VT minus 1, which reduces to IS. So this is a parameter that we usually get on our data sheets. So that's just our reverse bias saturation current, where the area is already taken into account, times the exponential of VD over VT, where we're making an assumption that our diode voltage VD is greater than VT, or our diode current ID is much greater than our reverse bias saturation current IS. And if one of these is true, the other one has to be true as well. So we really only need to make one of those distinctions. So for all intents and purposes, at this point, we're going to throw away this -1 because we're going to assume that whenever we forward bias our diodes or reverse bias our diodes, we're going to do it with voltages that are greater than 26 millivolts. So let's analyze a circuit using our Shockley diode model. Okay. So let's say that I have 1 milliamp of current. Like so. In parallel with a resistance R in parallel with 2 diodes connected in series like so. This is going to be diode 1. This will be diode 2. Our saturation current, IS1, and our saturation current, IS2, will be the same, 0.5 femtoamperes. So 0.5 times 10 to the negative 15. And we are trying to determine the value of R if our resistor current, IR, we'll label that here, is equal to 0.3 milliamps, and we will assume that our thermal voltage VT is 26 millivolts. So, anybody have any thoughts on how we might approach something like this? Yes. It behaves according to this equation. This is our diode current as a function of this diode voltage. IS is a constant, VT is a constant. So instead of having a nice linear relationship like we're used to with capacitors, inductors, and resistors, we now have a nonlinear relationship to deal with because of the exponential diode model. That's what makes these arguably a bit harder, Daniel.
Could try and find the current through the right side of the circuit by using current division.
We can't use current division. We can use Kirchhoff's current law for sure. Drawing a blank here. Jacob, I think you had your hand up a moment ago.
ID equation. I was going to say it's solved for DP by substituting ID in the relationship IR. So you can substitute out ID.
I'm not 100% sure that I follow. Let's use KCL first and see what shakes out from there. Okay. So using KCL, we know that our diode current ID1 must be equal to our diode current ID2. So I'm just going to call these ID because of the same thing, where ID is this current flowing through my two diodes in series. We okay with that? And using Kirchhoff's current law, that's just going to be 1 milliamps minus IR. For a resistor current of 0.3 milliamps, this then is 0.7 milliamps. So we now know what our diode current is. And Jacob has suggested that we can then solve for our diode voltage VD because we know what our diode current is. I'm interpreting what you were talking about correctly. Okay. All right. So I agree with that. So since ID is going to be approximately equal to IS times the exponential of VD over VT, we could rearrange this to find that our diode voltage VD is going to be VT times the natural log of ID over IS. Is everybody comfortable with going from here to here? All right. So that means our diode voltage is 26 millivolts times the natural log of 0.7 times 10 to the minus 3 amps over 0.5 times 10 to the minus 15 amps, which comes out to be 0.727 volts. Where can we go from here?
So the saturation current is going to be normal.
Yeah. If it isn't given, I have to give you enough information to calculate it using previous relationships and all of that kind of stuff. It's nothing more than the saturation current density that we saw for both PN junctions as well as metal semiconductor rectifying junctions multiplied by the area of the junction. Daniel.
So that's the voltage drop for one time. You say apply that to
Absolutely correct. Right. So we just figured out what this voltage VD is, and because our diodes are identical, the voltage drop across the resistor is exactly equal to 2 voltage drops across our diode. 100% correct. So, since VR is twice VD and IR is 0.3 milliamps, R must be twice VD over IR, or 2 times 0.727 volts divided by 0.3 milliamps gives us 4.848 kiloohms. Okay. So we worked our first circuit, not particularly difficult. So let's make it difficult. I can scroll back up if you guys need me to, but I didn't have enough room to do this problem here, so I scrolled down the next page. All right, so let's say that we have this circuit. Ten-ohm resistor. .5 amps. .50 ohm resistor. Here's our diode. Let's throw a 10-volt source down here. .25 ohm resistor down here. I'm going to define the polarity of my diode voltage as such, and the direction of my diode current, like so. Our goal is to determine ID and VD. By the way, just for argument, typically speaking, when we're solving for ID and VD combined, we call that solving for the quiescent operating point of our circuit. It might also be referred to as the Q point, and it's effectively just the stable DC operating point that the system is at. We're usually associating that terminology, Q point or the quiescent point, with diode circuits, particularly what the voltage across and the current through the diode is. We'll also deal with Q points for transistor circuits and all that kind of stuff as well, where we need to know what our terminal voltages are, as well as the current being carried by our transistor. So that's just a phrase commonly used when dealing with nonlinear circuits as a quiescent operating point. But anyway, so we're solving for these two quantities, effectively the DC operating point of the diode. If IS is equal to 5 nanoamps and our thermal voltage is equal to 26 millivolts. So who's got some thoughts about how we might approach something like this? I guess we could. Actually, no, we can't. Sorry. We can't use superposition. Because superposition requires our circuit to be linear. And a diode is literally a nonlinear device because the current through the diode and the voltage across the diode are not proportional to each other. So superposition is not fair game for diode circuits. We will do things to linearize them later on and all that kind of stuff to help us. But if we're going to use our exponential diode model, superposition is actually off the table. Can we do mesh? Absolutely. So let's call this mesh current IA. Let's call this mesh current IB. So let me ask a quick question here. We can't do superposition because we have a nonlinear circuit element. Are we sure we're okay doing effectively Kirchhoff's voltage law or Kirchhoff's current law? Yeah, because Kirchhoff's current law and Kirchhoff's voltage law have nothing to do with linearity whatsoever. They're the law of conservation of energy and the law of conservation of charge, respectively. They have to always be true regardless of what is in our circuit. Okay. All right, so let's do KVL around mesh B. So that's going to look like negative 10 volts minus VD plus 25 ohms times I2. And realistically here, we don't actually need to go through all of the steps of solving for or doing KVL around mesh A because we can kind of sort things out from here, right? We know that IA is just our current up top of 0.5 amps. Daniel, you had your hand raised?
Just for,
Yes, sorry. Erase. There we go. Thank you for that. Okay. So we also know, so this is a current relationship equation effectively. That our mesh current IA is half an amp. And we can see that our mesh current IA of half an amp is equal to our diode current ID plus our mesh current IB. And so we could rearrange this thing a little bit to find that IB is equal to 0.5 amps minus our diode current. So I'm going to substitute this relationship for IB into my first equation. And what I wind up getting is negative 10 volts minus VD plus 25 ohms times half an amp minus ID is equal to 0. And since I know that ID and VD are related to each other, I can get rid of one of these variables in that way. Lucas. IA, let me write this out here. It's flowing in, ID is flowing out, and IB is flowing out. So I feel pretty strongly that I did that right. And then I moved ID over from the right-hand side of the equal sign to the left. I moved it over with IA. So I feel like I have it correct. Okay. All right. So I will have negative VD, which is negative VT times the natural log of IB over IS minus 25 ohms times ID, excuse me, is equal to 10 volts minus 25 ohms times half an amp. How do we solve that? Yes, we are assuming that the thermal voltage is 26 millivolts, which was stated. Right. Okay, so you're correct to an extent. We have a one equation, one unknown system. Unfortunately, the algebra doesn't really work out in our favor to solve it algebraically, so we're probably going to have to use some sort of numerical solver. Luckily for us, all of our calculators have numerical solvers on them. That being said, every now and then, it's not going to work. So let's solve it iteratively first, which is literally just guessing and checking and seeing that we settle on some final answer. And then we'll use our calculators and make sure that they match. Just because I want to demonstrate the iterative solution process in case you ever need to use it. Taj. Realistically, you should be able to settle to something within 3 to 5 iterations tops. But on the exams specifically, I'm going to try to make it to where you don't, your calculator will be able to do it in one go, because that's just wasting your time. Okay. All right, so let's see here. So to make my iterative process easier, this is the relationship that I'm going to wind up using. Okay. So we could rearrange this equation to find that ID is going to be 2.5 volts minus VD divided by 25 ohms, right? So 25 ohms times half an amp. Let's see, what's that going to come out to be? 12.5. So 10 minus the 12.5 is going to be negative 2.5. So that's where that 2.5 is coming from when we move stuff around correctly and all that kind of good stuff. All right. So what seems, let me write this down. Iteration number 1. Let's make a guess. Let's start by guessing what our diode voltage is, because that's usually going to be the thing that doesn't change the most. Okay. So I would typically start, if you're not specifically told by what type of diode you're dealing with. And so by that, I mean, if you don't know if it's silicon or germanium or gallium arsenide or something like that, half a volt seems like a reasonable guess. Typically speaking, for silicon specifically, we could use 0.7 volts. For germanium, 0.3 volts. And for gallium arsenide, around 1 volt. So somewhere in the ballpark of the built-in voltage is usually a good starting place. Okay. All right. So let's say, since we're dealing with something generic here, we start with a guess of VD is equal to 0.5 volts. And now we solve for the quantity ID. So we'll have 2.5 volts minus 0.5 volts over 25 ohms. This comes out to be 80 milliamps. And so now for our second iteration, we're going to use that ID is equal to 80 milliamps to back solve for VD and see how far we were off, right? So VD is our thermal voltage VT times the natural log of ID over IS. Substituting in numbers to this, that's 26 millivolts times the natural log of 0.8 times 10 to the minus 3 amps over, I think, 5 times 10 to the minus 9. And we wind up getting 0.431 volts. So there was a pretty significant change between our iteration 1 voltage and our iteration 2 voltage, which means we've got to keep on trucking. ID is now going to be 2.5 volts minus 0.431 volts divided by 25 ohms. And this comes out to be 82.748 milliamps. So we're not too terrible. And then we'll just repeat this process until effectively the numbers don't change or we're okay with the tolerance. Hannah, yes. Yeah, 80 times 10 to the minus 3. Thank you. Yep, I just wrote it down wrong. I put literally in my work 80 milliamps. I wasn't putting everything in terms of base units. So just total brain fart. Thank you. So for our third iteration, we're just going to calculate for VD again. So that's going to be 26 millivolts times the natural log of 82.748 times 10 to the minus 3 amps divided by 5 times 10 to the minus 9 amps, which comes out to be 0.432 volts. And ID was 2.5 volts minus 0.432 volts. Divided by 25 ohms, which comes out to be 82.713 milliamps. And we could keep going on and on and on if we wanted to, but I would argue that since our change in our voltage is literally a millivolt, we're probably good to stop. So that's one way to do it. It is the long and tedious and annoying way to do it, but sometimes we'll be faced with having to do it in that way. Now, please take out your calculators and use your numerical solver and see what you get. Grayson, what's up? I don't know how that's possible. What the hell is my calculator? So I'm going to do this on my TI using my numerical solver, that second sign. And let's see, I'm going to scroll up here and I'm going to use this second relationship. So negative 0.026 times the natural log of x divided by 5 times 10 to the minus 9. Minus 25x will be equal to negative 2.5. Solving for x, I get 82.714 milliamps, which is pretty darn close. And then using that relationship, let's see, VD would be 0.026 times the natural log of x divided by 5 times 10 to the minus 9, 0.432 volts. The numerical solver got us there quicker in this particular case, but again, sometimes we just can't rely on it. Okay. All right, so one of the things that I was trying to show you guys with that iterative process is that sometimes analyzing these circuits using the Shockley or exponential diode model can be a pain in the ass. So we might want to use a different model that's a less of a pain in the ass. Okay. So now let's talk about the ideal diode model. So in a conventional or in the exponential diode model, our current voltage relationship looks something like this. Where under forward bias conditions, our voltage exponentially increases, or excuse me, our current exponentially increases as our voltage increases, right? So this is the exponential diode model. And then the ideal diode approximation is as follows. So here's current, here's voltage. That's our ideal diode model. Effectively saying that our diode is a unidirectional valve for current flow, meaning that if it's reverse biased, no current flows whatsoever. And if it's forward biased, any amount of current that we need to flow can flow. And the voltage drop across it is effectively zero. So it's either an open circuit or a short circuit. So actually, let me move this over to the side. Sorry. Give myself a little bit more room. So when ID is greater than 0 volts, VD is exactly 0 volts. Means we replace it with a short. And when VD is less than 0 volts, ID is 0 volts, meaning under this case, we replace it with an open circuit. So fairly accurate to say it behaves similar to a switch. Absolutely. It should be fairly obvious, but this model is going to introduce a bit of error into our equations. Let's see how bad that error is. So yes.
Very good.
Yep. So subscript D means something to do with diodes. Absolutely. So, sorry. Let's rework our previous circuit. And first, I want to show you how the ideal diode model can be used to determine kind of the logic state of a diode. So we are going to make an intentionally erroneous assumption that our diode is effectively off or reverse bias. We know that isn't true because we just found that there is a positive voltage drop across it and a positive current flowing through it when we use the exponential model, right? But we're assuming it to be off here just to illustrate how it can be used. So this would be our diode voltage VD, like so. So I'm going to put number 1 here. Assuming diode is off. If we wrote a KVL equation around this loop, we would see, and I'm going to use this bottommost loop right here, negative 10 volts minus VD plus 25 ohms times half an amp is equal to 0. Solving this expression, we find that VD is equal to 2.5 volts. How do we know that our assumption that our diode was off is wrong, given these results? That has nothing to do with this. In the ideal diode model, the voltage drop across the diode is going to be, so we are assuming that our diode is off. Effectively, we are assuming that our diode is reverse biased. This voltage is positive. That's a problem. That's how we know this diode is not off. Okay. So now let's run through things really quickly with the diode on, and we should see that the current flowing through the diode is a positive number, which will tell us that our assumption was correct, right? So under reverse bias conditions, we replace our diode with an open circuit, and then we solve for the diode voltage. If we get a negative voltage, we were correct. If we get a positive voltage, we were incorrect in our assumption. Now, let's assume the diode is forward biased or on. So we're going to replace our diode with a short circuit. This is our diode current ID. All right, so how are we going to solve for our diode current here? And please, for the love of God, don't say no. Smart asses. Let's oops, I accidentally erased the 50. So let me ask you guys a simple question. What's the current flowing through the 50 ohm resistor? 0.5 amps. Great. What's the current flowing through the 25 ohm resistor? 10 over 25. Using these results, ID is 0.1 amps. Is this okay? Absolutely. That's a positive number, right? So if we assumed on and we were incorrect, we would expect to get a negative current. Okay. How close is this model to what we found using the exponential model? 20% error. So not horrifyingly off, but still not super great. We'll come up with a middle ground model here in a moment. But this really illustrates kind of the best use of the ideal diode model is determining when diodes are on or forward biased or off or reverse biased, because they're not really like resistors, capacitors, and inductors. So it's going to take us a minute to get an intuitive understanding of what we should really expect. Okay? So let's look at another circuit here where we're literally just trying to figure out which diodes are forward biased and which diodes are reverse biased. Could you repeat your question, please? So the whole point is to not have to use the exponential model at all because it's cumbersome, which is what we'll be getting to when we get to the, think of what I called it here, constant voltage drop model here in a moment. But anyway. All right, so let's say that we have the following circuit. Six-volt source. Just as an explicit heads up here, in your homeworks, exams, etc., and this should be kiloohms, I will tell you specifically what diode model to use for each problem so that there's no guesswork. I'm telling you explicitly, use the ideal diode model, use the exponential diode model, use the constant voltage drop diode model, etc., and then you'll get practice with all of them. All right. So this is our circuit. We have a 5 kilo ohm resistor. We have this diode D1. Here's a 4 kilo ohm resistor. 8 kilo ohm resistor. $10 source. Here's our diode D2. I'm going to define VD1 like so, and ID1 like so. I'm going to define VD2 and ID2 like so. And I'm going to give you guys just a moment to decide which diode is on and which diode is off while I text my wife. In class. Okay. So, Nathaniel, do you think, Nathaniel Dubois here in the front row, do you think diode 1 is on or off? On, okay. So let's assume diode 1 is on. Haban, do you think diode 2 is on or off? On, okay. So let's find out if that is correct or if it is not correct. So with diode 1 on, we're going to replace diode 1 with a short circuit. Don't know why it's lagging all of a sudden. And with diode 2 off, we're going to replace it with an open circuit. So stop lagging computer. So here's our current ID1. Here's our voltage VD2. So what's ID1 in this case? 2/3 of an amp. 2/3 over 2/3, excuse me, 6/9,000, so 2/3 of a milliamp. Sure. Okay. So 6 volts over 9 kilo ohms is 2/3 of a milliamp. Okay. So it seems like our assumption that diode 1 was on is correct. What's VD2? So I don't think it's going to be 0. All right, so what's the voltage drop across the 8 kilo ohm resistor? 0 volts. So the positive polarity terminal of this 10-volt source gets to move all the way over here because there's no voltage drop across the 8 kilo ohm resistor. So the positive polarity terminal of the 10-volt source is the negative polarity terminal of VD2. The negative polarity terminal of the 10-volt source is at the positive terminal of VD2. So VD2 is negative 10 volts. Does this mean that our assumption about the on-off state of diode 2 was correct? Absolutely. So we got it. First go. Yay for us, or for Nathaniel and Haban. Okay. So the last model that we're going to talk about today is the constant voltage drop diode model. And it's kind of the middle of the road Yes, Ryder. The current's positive. That's it. So if the current's positive, it's correct. If we had made an incorrect assumption, the current would have been negative, which can't be true for a forward biased diode. And if this voltage here were positive, that can't be true for a reverse bias or off diode. So we're literally just looking at the sign of the diode current. If it's positive, the diode, and we assumed it was on, we were correct. If the sign was negative, we were incorrect. When we're looking at the diode voltage, if we had gotten a positive voltage, we would have been incorrect because we replaced it with an open circuit, which is appropriate for a reverse bias. Grayson, let me answer your question first.
So say if we do correctly on one of the diodes or off, would that affect our outcome of our assumption on like on one of the other diodes?
Really, really good question. So for a simple circuit like this, probably it'll work out in your favor that if you made one correction or one assumption wrong, fixing that would go right. Let me look back through my notes here really quickly because I solved it all 4 ways. So page 4, there we go. So the first time that I solved it, I assumed that diode 1 was on and diode 2 was on, and I found that diode 1 being on, the assumption was correct. Diode 2 being on, the assumption was incorrect. So it seems to bear that assuming that diode 1 on and then getting the other thing wrong tells you that just switching the other thing would get you fixed. When I assumed that diode 1 was off and diode 2 was on, both assumptions came out to be incorrect, which is exactly the opposite of what we had here. And then when I assumed, let me go to page 5 here, that when both were off, the diode 1 assumption was incorrect and the diode 2 assumption was correct. So for this particular circuit, it did work out to where whichever one we made the mistake on, changing that one state worked out. That being said, for a more complicated circuit, I don't think it's true. Realistically though, I'm not going to give you anything more than a 2 diode circuit to play around with just because it's wildly tedious. You're not really getting a whole hell of a lot of value of just like if you had a 3 diode circuit, that would be 9 permutations that you would have to potentially deal with of on-off states for every diode to get everything figured out. That's a pain in the ass of just repeating the same basic calculations over and over and over again and checking the signs. So I'm not going to be mean enough to do that. But realistically, you couldn't say, you know, if you had a 3 diode circuit and you guessed that all 3 were on and just one of them was off, that doesn't necessarily mean that you just changed that one thing. Daniel.
Does the orientation of the
For sure. Yeah. So, I mean, realistically, the positive polarity terminal of this diode was connected to the negative polarity terminal of this voltage source. That's probably going to be a reasonable indication that this diode's not going to be on, because that would mean that, so actually, let me go back a very small stitch here. This 10-volt source is larger than this 6-volt source, so we should assume that this is probably the thing that's supplying power to the whole circuit, which means the current flowing through this thing is going to be going from the negative polarity terminal to the positive polarity terminal, which means we would be expecting a positive current to be flowing through a reverse bias diode, which doesn't make sense. Right? So that's a good reason to assume that this one has to be off. For this one over here, positive polarity terminal with the positive polarity terminal, negative polarity terminal with the negative polarity terminal. There's some resistors in the way, so that's a reasonable way to think. It's probably on. So you can develop an intuition that'll help you, but you still kind of need to go through and check things. All right, constant voltage drop model, and then we'll get out of here for today. So the constant voltage drop model is a compromise between the Shockley and the ideal diode models. So I'm going to draw the curve for Shockley diode model again. So here was our diode current, our diode voltage. And then our curve looks something like this. The constant voltage drop model is as follows. So here's ID, here's VD, and we're going to see that our current is 0 up until some point at which our current turns on. And this voltage we're going to call VD on. And the value of VD on that we are going to use is dependent on the material that our semiconductor, our diode is made of, excuse me. So left-hand column of this table is the semiconductor material, right-hand column is the on voltage. For silicon, 0.7. For germanium, 0.3. Gallium arsenide, 1.2 volts. So these assumptions are, again, very close to the built-in voltage for a silicon PN junction, a germanium PN junction, and a gallium arsenide. So for a forward biased diode, so where ID is greater than 0, we're going to say that our diode voltage is literally VD on, meaning we replace our diode with a voltage source having a value of VD on. And for a reverse bias diode, so ID is less than 0. Sorry, VD is less than 0. We're going to say that ID is equal to 0 and replace with an open circuit again. And so very quickly here, let's rework that example problem a third and final time and see how close the constant voltage drop model is to our exponential model. James. Realistically, yeah, but we're just going to say that we're assuming reverse bias conditions. Yeah. Putting too much thought into it. No, I understand the logical argument there, but the only way for us to know if VD is less than VD on is to literally analyze the whole circuit using the exponential model and figure that out. So we're making a generalization here. If we believe the diode is forward biased, replace it with a battery. If we believe it's reverse biased, replace it with an open circuit. Because we can't check whether or not VD is greater than or less than VD on unless we analyze the whole NIM thing. All right, so boring circuit, third time's a charm. 10 ohm resistor, 0.5 amp current source, 50 ohm resistor. Here's our voltage VD on. 10 volts. 25 ohms. Here is our diode current ID. Let's assume that VD on is approximately 0.3 volts so that we have a germanium diode. And it should be fairly obvious to see that the current flowing down here is just going to be 10 volts plus 0.3 volts divided by 25 ohms is 0.412 amps. And the current flowing down right here is 0.5 amps. And so our diode current is simply the difference, which is 0.088 amps or 88 milliamps, which agrees much more closely to the exponential model without having to do all of the work of using the exponential model. All right, that's enough out of me. On our next class meeting, we are going to talk about small signal diode model, effectively how we can linearize a diode. Why are you shaking your head no?
I don't.
Small signal models where things are interesting. Large signals is boring as shit, man. So, so we're going to start dealing with the small signal diode model. So effectively, we're going to look at what happens when we perturb our circuit away from its DC operating point by a small amount. And we can use that concept to effectively linearize our circuit as a small signal and get to use just conventional circuit analysis techniques in our analysis. So that's what we have on the table for Friday. Thank you. All right. You guys have a great rest of your day.